Okay, so I think we can start. So it's really, first of all, we would like to apologize for these problems with the organization, but everything was done really at last minute. And it's really a pleasure to have Ricardo Schiappa from University of Lisbon. And please, the stage is yours. Thank you very much.
Thank you. Thank you very much for the invitation. I'm really, really sorry about this mess with the airport. So it's the first time that I cannot attend a talk I'm supposed to give. So it's quite embarrassing. And in fact, at some stage, I thought, well, it's the first time I'm actually going to fly for work after COVID. And then Air Portugal said, no, you're not. So I'm sorry about that. Anyways, so I will be giving these first lectures online. There is no other option. Feel free to interrupt at any time. I mean, today, I'm sorry, I'm seeing some rather senior people in the audience, and it's going to be extremely basic and elementary, so it might be slightly boring for the most senior people. And for the younger people, please make questions at any time, no problem, interrupt me, so on. I'll be happy to answer everything in real time. So what I will be mostly covering as well is the physics report we had, when is this from? 2019, 2 years ago. I will share it now so you can look at it. And I suggest that if you really want to follow the lectures carefully, that you just basically complement the online video with this. By the way, it was written with Inês Aniceto, who is now in Southampton, and Goshke Bazar, who is now in Maryland, if I'm not mistaken. And just complement whatever I'm going to tell with what's going on here. And in fact, I will give one or two homeworks of stuff that was worked out here, so you should go and take a look. And by the way, this is of course on the archive, so it's free downloadable. All right, so let's get started then. So let me move to the iPad. Let's turn it on. Okay, so here we go. So hopefully everything is good. Let me just make it smaller. All right, so what do I want to talk about? I want to talk about the following. I keep getting warnings, by the way, of people entering the room. I want to talk about the following. When we're, let me make a comment. When we're computing observables in whatever theory we might be interested in, and this includes quantum mechanics, this includes quantum field theory, this includes string theory, basically whatever you want, most observables are, you can just reach them via perturbation theory. I mean, exact results, of course, there's lots and it's very important, but they're not commonly reachable. The issue with perturbation theory is that whenever, well, not, again, this is also not always true, but whenever the problems are interesting in a way that hopefully will be explained throughout. Okay, this blue is not a good color. Let me pick a brighter color. If interesting, whatever we want to compute, and by the way, maybe I could have written here, we can compute the energy, some whatever, quantum mechanical problem, we want to compute the free energy, we want to compute the partition function, whatever it is. So if these observables are interesting, then perturbation theory has 0 radius of convergence, which means that it basically doesn't converge anywhere. So we're dealing with a divergent series. And divergent series have been known in math for quite a while. In fact, as far as I can tell, the first instance that somebody complained about them was the mathematician Abel, who unfortunately didn't live long. And in 26, he said the following, and I think it's worth writing it here. Divergent theories
Recording stopped.
are, there seems to be a problem with the recording. I just got well, divergent series are the invention of the So I guess it didn't start very well, right? And so we should be warned on how to proceed. But given that, well, even if not in person, at least online, I'm giving lectures in France. We're going to do like the Frenchmen said. And a few years after Abel, Borel came along. He had a much longer life than Abel. And he said, no problem. No problem. So we're going to follow Abel, and I can already give you 2 instances of divergent series you might have seen at some stage. And we can actually sum them. So the first one is this one. I have these 2 examples here, which looks pretty bad. This is not in the class of problems that appear in field theory and so on, but if you sum this, you get 1/3. So that's pretty reasonable. And here's another one, which is in the class of problems that we will look at. This one's also pretty bad. And if you sum this, you get this number. Well, it's an irrational number. So we're going to be very pragmatic, and we will not worry about devilish issues or Abel's complaints, and we will follow Borel and say, okay, we can do it, let's do it. And let's understand also why we can do it. So you can see that these 2 series I have here are slightly different, because if I compute, I'm gonna have to go slightly up, let me just leave this one here. If I compute actually the radius of convergence of this series, so of course, by the way, I just wrote them here as series and not as power series, but to compute the radius of convergence, I have to just extend this to power series, but this is of course elementary, so I just have to put the next to the end there, the next to the end there, and then this would be a function of x, which, for illustrative purposes, I'm still not showing, but let's go on, and let's just leave that one there. So if I consider this power series, and then the radius of convergence, let me just use the standard complex analysis. Well, I can actually immediately do the calculation. It's basically 0. So this doesn't converge anywhere. This is known as an asymptotic power series. All right. So what are we going to do with these things? All right. So that's sort of the mathematical first words. Let me also give you some just physical first words of what goes on in physics. In physics, we have to compute sometimes some observable. Let me just denote it like that. Doesn't matter what O is. And let's imagine that all we can do is perturbation theory. So I'm going to call the perturbation theory of this object the following way. Phi with naught, and the naught will mean that I'm doing perturbation theory, that I'm looking at the perturbative sector. And these will have, I'm going to compute this in whatever way it is. So maybe I'm using, I don't know, Rayleigh-Schrödinger perturbation theory. Maybe I'm using, I don't know, Feynman diagrams. It doesn't really matter. In fact, whatever way it is that we compute stuff, I will never be worried about it. I'm just going to look at what to do with the perturbative series once I have actually done some computation. And so at each order in perturbation theory, I'll call the order in perturbation theory K. The the coupling constant, let's just put an H bar, it doesn't matter. And then I have to sum in K. But what I'm really concerned right now is about these guys. Everything else I'll forget. It's just for notation. And in most of the problems, again, quote unquote, interesting problems, what we find is that these guys, they scale as K factorial. And you say, okay, that's sort of good and bad, right? I mean, it's interesting. Abel didn't like it. Borel was okay with it. So let's see, what can we do with this? And the first thing you can ask is, okay, that's the leading growth of these guys. Can I say anything else about subleading, next to leading, next to leading, and so on the growth of these guys? Already a long time ago, research on instantons had said that, yes, actually, you can say something because the next to leading guy is associated to instanton. And by the way, I will always use the word instanton, but of course, in some quantum field theory problems, the correct word to use would be renormalon, but let's not go into that. Again, let's be focusing on what's going on with the growth of perturbation theory. And you say, okay, that's interesting. So that's a novelty. It's telling me something about, non-perturbative components of these observable I'm trying to compute. It's telling me something about instantons, or again, in quantum theory, maybe about renormalons. And those, of course, are always harder to understand because of their semi-classical decoding. So what else can I find looking at more subleading third in these growths? Well, it turns out that we will be able to actually find a lot of stuff. And so when I look at the growth, when K is much bigger than 1, I'll be able to say everything about this guy by looking at multi-instanton sectors. So let me just schematically write it like that. So there's contributions coming from the one instanton sector. Everybody is going to contribute. Then there will be people coming from the 2 instanton sector. Everybody is going to contribute, and so on and so forth. So that,
no, perché
guys, yes, is there a question? Maybe not. So that all these guys will contribute to predicting large order growth. Right? And we've already seen that here. So sort of the one instanton sector is predicting something about the large order growth of the perturbative sector by telling them that, or by telling us that, well, yes, there's a leading factorial growth, but then there's a subleading. The next leading growth is exponential, and it's dictated by the instanton action. And then there's going to be more, and we'll see how more people will come along and play the game. But this is not the only way to look at things. So another way, let me leave this one here. Another way that you can think about what's going on, and this will be resurgence relations that we'll discuss in a second, is that you can look at, let me write exactly the same on the blackboard I would lead, but here I guess I less scrambled if I just write it this way, is that we can think about these arrows as going the other way. So instead of predicting the large order growth, I am decoding the large order growth. And what do I mean by decoding? I mean that by, if I, for some reason, I have, with Feynman diagrams, maybe that's not very efficient because the number of Feynman diagrams that I have to compute also grows fairly fast. And so I can't go very deep in perturbation theory, but there's other problems that maybe we'll discuss in later lectures. When we start going into more advanced material, there's other problems where I can actually efficiently compute a lot of perturbation theory. And then I can use all these perturbation theory to very large orders to decode the non-perturbative content and find what they have in mind. Okay, thank you. What I was saying is that in some problems, I can actually generate a lot of perturbative data. And then I can, and I am not sure, because you can always say, how sure am I that I have actually completed all non-perturbative content of a theory that I'm looking for? I'm not sure if, there's only instantons, there's only renormalons, there's more stuff. In string theory, there's D-branes of different kinds. Do I have everything? Am I missing something? And so by, going deep into the large order, I can try to see whatever is missing and decode all this semi-classical information. So that's sort of the idea. Now, let me say something, which is that what I've written here was for the perturbative sector, but I could have, written here any non-perturbative sector. And of course, then all these guys would have to be changed accordingly so that this sort of large order relations can be written for anyone, for any sector of the theory. So if I'm in the 5 instanton sector, if I'm in the 17 renormalon sector, I should be able to write these large order relations, and resurgence will relate everybody to everybody else. So let me write that here. Resurgence relates everyone to everyone else in this sort of way. So this is very good because, we start looking at one sector and we can go around and see other sectors. So that's the idea of resurgence. Let me also just tell you that we will need, let me see, 2, okay, I can do that now. We will need 2 more ingredients that we will, and as I said, today's lecture is going to be extremely elementary. And we're just going to be looking at the names that we need to get used to and so on. And then we will be visiting these things in circles. And as we go around in the merry-go-round, we will understand better and better what are all these names we're talking about. Anyways, so resurgence is this sort of theory by, should write here, Ricardo is also French. We keep the trend of the French mathematicians. And it needs 2 more ingredients. Maybe I should write here. This is circa 1980. Trans series and bridge equations. So these are also names we're going to be seeing in the following. And so trans series is basically an object that puts everyone together. So I have all these sectors, perturbative, non-perturbative, instantons, renormalons, D-branes, whatever. I assemble them all together in an object known as a trans series. And of course, the name is sort of obvious. It's, when I'm doing perturbation theory, I am writing down an asymptotic series. And the trans in trans series is just saying, okay, let me put everybody else beyond perturbation theory, everybody who's hiding beyond all orders, come along for the ride. So if you're an instanton, if you're a normalon, if you're a D-brane, you will not be a standard power series. We'll see that you will get a contribution, which is basically known as a transmonomial. And please come along and join us, and then we can relate everybody to everybody else. And the exact way in which everybody is putting together is because of the bridge equations. Tells us how to relate everyone. So the exact way in which things relate to each other is essentially dictated by the bridge equations. Okay, so we'll see what these things are. The final sort of introductory thing I want to say is that when I wrote these relations of large order relations, if you want, telling us how to relate sectors to each other, I told you, well, the perturbative, I can relate it to all these non-perturbative sectors and any non-perturbative sector to anybody else. This actually requires 1 more ingredient, and it's actually quite important non-trivial ingredient, which is when I write this sort of formula. Let me write it once again, sorry about that. But on the iPad, I don't want to be making a big mess. This is not the whole story. So there's actually some numbers that appear, which are basically Stokes data. this is, you could have problems where the trans series looks the same, where the bridge equations look the same, yet the problems would be different. And so there must be, of course, if the problems are different, all these factors, perturbative and non-perturbative, if you look at, each, where was it? I wrote it. If you look at each of these guys here, of course, they will be different. But that's not the whole story. Another thing that's going to be different is Stokes data. Okay, maybe I should go back to the Stokes data. And this is quite hard to compute. And hopefully in one of the last lectures, I will tell you how to compute Stokes data. Resurgence Stokes data. So, I mean, there's some sort of easier Stokes data to compute. There's some sort of harder Stokes data to compute. And we've recently actually managed to compute all these things for point 1 and point 2. And hopefully I'll give you a little flavor about that. But that's going to be next week, not today. All right, what else? Is there anything else I should say for introduction? Yes, there's another thing I should say, which is the following, is that the Stokes data, of course, comes back from the 18, red is a bad color, I guess. If I'm not mistaken, maybe this is not the exact number, but I think this was done in 1859 by Stokes, which is, he was studying the rainbow as described by the area function, and that's how he came along with Stokes phenomena. And of course, that the reason why we're calling these guys Stokes data is because they're related to Stokes phenomena. And so what's the idea of Stokes phenomenon is we go back here to our trans series. Our trans series putting everyone together. And okay, I don't have enough room in one board. Everyone means two kinds of people, perturbative people and non-perturbative people. And the non-perturbative people are not immediately seen by the perturbation theory. I mean, this was already known from Poincaré, right? These guys are beyond all orders from the point of view of perturbation theory. So if you want, perturbation theory is sort of, let me change this color, is associated to blue is a bad color. Sorry about that. Components like that, and let me do it again because I've been using H bars just to be consistent. And these guys would be exponentially suppressed, where remember H bar is small. So they really, it's the exponentially so suppressed that it's beyond all perturbative orders because this object is not does not have a power series at the origin. However, it's not the case. I mean, this is definitely the case when H bar is real. This is not necessarily the case as I start taking H bar around the complex plane. And so, whereas a perturbative component of my trans series is bigger than a non-perturbative component of my trans series, when I am a real positive standard physical region of my parameters, it could be the case that I move around the complex plane, things change. And in particular, they can change dominance. And so who was perturbative is now, from the point of view of the whole trans series, suppressed, exponentially suppressed. And who was non-perturbative might now become, from the point of view, that was not the question mark, by the way, that was a exclamation mark. And who was non-perturbative from the point of the trans series is no longer exponentially suppressed, but can become exponentially enhanced. So they sort of change dominance, and that's the origin of the Stokes phenomenon. That's something that you can see if you have ever seen the area function. On the positive real axis, it's sort of exponentially suppressed, but on the negative real axis, it oscillates, like cosine oscillation. And that was the origin of Stokes phenomenon. From the point of view of the trans series, it will also actually be quite simple to observe how it comes about, because the trans series is sort of being very schematically monomials plus a trans series parameter, let me call it sigma like that, times the exponentially suppressed people. And Stokes phenomenon, this change of dominance, is sort of telling us, this will of course all be made much more precise, that sigma is jumping at Stokes lines, I'll tell you what those are later on, by Stokes data. And this guy here is the same guy there. Okay, so these guys will be the same. So whatever I find in large order is also going to be controlling for me Stokes phenomenon, basically. The final thing that we will be talking about in these lectures is resonance. And whereas this is not really a very fundamental thing when you first start looking at resurgence and all these things, even if you're looking at quantum mechanics, well, yeah, let's stick with that. Even if you're looking at quantum mechanics, quantum field theory, it's not really something that you say, well, this is fundamentalist to look at, but it is in basically every string theoretic, and hopefully we'll make this clear in next week or the other week, I forget when the other lectures are. Every string theoretic system you want to look at. So what's the problem here is what happens if you, instead of having a single instanton action, you have more. So the exponential terms in the trans series, they come usually, no, that's not what I wanted to do. I want this guy. They come usually with an instanton action there. But what happens if I have more than one instanton action? And I look at arbitrary multi-instanton contributions, and M. Then something interesting could happen, which is I could have, not necessarily, but I could have problems where there will exist N and M such that this combination is 0. If that happens, then what was, from the point of view of the trans series, exponentially suppressed or enhanced, but whatever, becomes of order 1. And so it starts sort of mixing with the perturbative series. So this appears in every string theoretic example we've looked at. And so it's something also that one needs to deal with. All right, so this is sort of just some ultra generic first words on the subject. So what I'm planning to do in these lectures is the following. So today, and well, yes, I think probably also on Monday, we're going to be looking at a toy model, which is what I would call a Quartic integral. I'll tell you what it is a little bit later on. And this toy model will allow us to, introduce all notions that we've been discussing so far. Then after that, I want to talk about, and this will be, well, it will become clear that it's sort of a simple trans series. Then this is sort of the main topic. Let's see how long this takes. Then the second topic I would like to talk about is complicated, or no, let me not call it complicated. Let me call it generic trans series. And their bridge equations. And we need to discuss this generics, which might be a little bit formal, a little bit less physical, but we will need to do this so that then we can do the last topic, which would be a physical application. So this is the idea of, let's see how exactly we can split this in these 4 lectures. But that's sort of the idea. So I don't know if there's any questions so far. Otherwise, I guess I will just start with the first topic. Okay, so let's start with the first thing. Buddy. has any questions. So let's consider, what did I call this? Time model. Quartic. All right, so again, as I've already said, we are interested in computing some observable, fine. Some observable that I'm not worried about what it is. And I'm going to include a coupling constant, which I'm going to call X. And I will take X to be small. So this could be H bar, it could be G string, whatever. So let's write down a perturbative series. I already said that when I include that subscript 0, I'm talking just about perturbation theory. And I compute coefficients. I'll put the G there, doesn't matter. X, and this is just conventions, G plus 1. Okay. And then I try to sum everybody. And as I already said, the series is asymptotic, which means that the phi g's are growing factorially fast. So this is not going to converge, and we're going to use this notation to denote asymptotic series. Okay. So the phi g, they grow factorially fast. So the radius of convergence is already discussed. So what do I do? So this is when Emil Borel came along, and he told us, well, let's just introduce a transform, which now is known as the Borel transform. Which, by the way, those examples I showed at the beginning, these two sums, they're trivially and immediately done with Borel transforms. And so once I just tell you what it is, this would be sort of the first homework that I would recommend that the students would try to do, would be just go to Mathematica, use the prescription of Borel transform that I'm about to say, and compute this 1/3. That won't be very hard. That's actually almost straightforward. And then compute this number. And I told you that this was an irrational number, so maybe you can give me the analytic formula for it. It involves the error function. Wait, where are we? Here we are. Borel transform. So what does the Borel transform do? I will denote it with this curly B letter, and it moves from formal power series in X to formal power series in a new variable S, which I'll just call the Borel variable or the Borel plane. And it's very simple. Basically, it grabs some monomial here, and the Borel transform of this monomial is basically given by the following. So all these plus ones or minus ones are basically just conventions, and maybe, well, certainly if you guys read the physics report carefully, there's going to be a section that's going to tell you about all these possible conventions that I can have for Borel transforms. It's technical, so I probably will not cover it, but if you're interested in these conventions, it's discussed there. And so you see that basically what is this doing is an absolute triviality. I mean, this is there's factorial there. I mean, the reason why I'm using gamma functions, because not necessarily it's the case that always this alpha is an integer. You could have power series expansions in non-integer powers of the coupling constant. But anyway, so you have the gamma function there. It's basically killing the factorial growth. So this is almost a triviality. It says, oh yeah, you're worried that this grows factorially and you have a radius of convergence which is 0. Then let me kill that factorial growth. And now I have exponential growth, and exponential growth has non-zero radius of convergence. So this is...
Sorry, Ricardo.
Yes.
Do you have some sort of integral transform formula for this Borel transform?
Sure. Maybe we will. I mean, this is also again discussed in the physics report. I'm not sure I want to go with that. That's sort of more technical things. But sometimes you can play with path integrals rewrite path integrals in such a way that they look like the Borel resummation. I'll come to that in a minute. The Borel resummation of something else, in which case you can identify the Borel transform immediately. This is generically true when you have, let's say, more simple problems, problems that can be solved in other ways.
Sorry,
Anyway,
what I meant,
yes.
maybe it's stupid, sorry. What I meant
No.
is that
Ask anything.
you're
please.
telling me how the Borel transform acts on these monomials.
Yes.
I mean, can't it act on an arbitrary function of x?
No. Okay, so just hang on. No, that's not how it. Well,
Okay,
I mean, in
sorry.
principle, yes, you could say so if that arbitrary function of x has a power series expansion. But that's not the way we want to look at it, because the way we want to look at it is starting with this perturbative series where I really don't know what this object is. It's got radius of convergence, which is 0, and I really can't say anything. If you tell me, is this a function of x? Well, maybe. Well, hopefully, because I'm trying to, compute something which would be physically observable. So I hope it is a function of x, and I can actually compute a number to go into the lab and measure it. But I have no idea at this stage what that function of x is. So it would be very hard to say anything straight off, unless you resort to what I'm about to tell you now, in which you go through this procedure where you attack this thing monomial by monomial. Because, what actually is going to happen is that if I do the Borel transform as I've been showing you here, and I transform each of these guys, I'm going to produce a new series out of the perturbative series. So I start with this perturbative series that I had. This was really bad because I didn't know this guy here, right? It doesn't converge anywhere. I cannot say anything. But I have now Borel transformed it to this new series. And because I killed the factorial growth, this has at most exponential growth as a power series. And so I can basically compute it as a function. Or if you want, as a germ of a function. So what's going to happen, let me make a little plot here, is that if I'm on the Borel plane, then this object is going to have singularities, maybe, but the singularities are not going to be close to the origin. Just because I already removed the factorial growth. I only have exponential growth. So I have a non-zero radius of convergence. So I have a non-zero radius of convergence. I'm sorry, this should be a circle, but okay, whatever. And so I can compute my Borel transform here. That's good. So there I know Borel. Okay, I'm sorry, blue is not good. I keep putting blue. And then I can try to do analytic continuation, avoiding the singularities to go somewhere else. And then I sort of construct here. Yes, I construct a function. But we'll come to that in a second. The function does have singularities, so we'll have to see what to do with those singularities. So now I have a function by analytic continuation. But that's not what I was looking for, right? You could say, well, I was looking for, no, it's actually here. I was looking for this guy. How much is that guy? Well, then Borel says, no problem. Let's just invert what I did. So I started out with something which was highly formal, which was this, because given that it does not converge anywhere, I can't say anything about it. I removed the bad part of it. I computed a function. Let me just invert the operation that I did here. And that's known as Borel resummation. I mean, sometimes you can call Borel resummation the whole procedure that I am sort of explaining for you. And so I started out with this guy. That's the guy I want to know as a function. Let me leave it in white. That was bad, but then I can sort of Borel resum by inverting this function. It's just a Laplace integral now. And that should be the answer. There's, of course, some things to say, which is where along, so I was here on the complex, can I put yes? I was here on the complex plane and I need to choose a path of integration. Let's say that I choose that path. So I start at 0 and I go up to infinity along the theta direction. Then I put a theta there as well. All right, that's it. Lectures are finished. Well, not quite, because what happens if the path of integration that I pick hits the singularity? This is bad. I can't do the integral. So we still need to deal with this, and this is where basically the whole story starts. Let me do that plot once again. I'm on my Borel plane, and I have a singularity. I'll talk about the nature of the singularities in a second. And I want to do my Borel resummation, and I'm good there. I'm good there, there, but of course, it's going to be an issue if I'm doing this. And so this is known as the Stokes line. This rate of integration on the Borel plane where I hit singularities of my Borel transform. And I need to decide what to do if I hit a Stokes line. And basically, the integral is not defined. So how shall I work this out? So the way to do it, and again, we'll see this much more carefully, is to just define this resummation just to the left, which I'll call theta plus, and this resummation just to the right, which I'll call theta minus. And this will be known as lateral Borel resummations. Actually, let me write them slightly differently, like this. Lateral Borel resummations, okay? And so I can do anything up to theta minus. I can do anything from theta plus on. I can't do the theta one because of the singularity. But there's actually, it turns out that there's something fascinating which occurs here. Well, I guess I can just look at the picture, which is that they're related. It's not like they're, you know, random stuff. So S theta plus and S theta minus, these two lateral Borel resummations, and maybe I should, sorry, for the formula that's coming, this has to be closer to here, theta minus, and they're actually related. So what happens is that they're not the same, but they're almost the same. So there's an object that tells me how to relate these two lateral Borel resummations. And let me just try to have as much as possible in the screen. This is known as the Stokes automorphism. And this is going to tell me how to jump Stokes lines. And you say, jump Stokes lines, that rings a bell. And in fact, if we go back to when I started the introduction, and I was telling you about Stokes phenomenon, there were some jumps. Transverse parameters were jumping because of Stokes phenomenon. Whenever I crossed, when there was this change of dominance, whenever I crossed, now I can be more precise, whenever I crossed a Stokes line, there's a jump. And that jump, it will be precisely encoded in this Stokes automorphism. So, I mean, we're starting to be more rigorous about what all these things are about. And well, now it will be slightly mystical what I will say next, but we will hopefully, well, let's see. Almost 1 hour is gone. Let's see if maybe still a little bit later on we can see, is that the Stokes automorphism actually turns out as an automorphism. Of course, it's the exponential of the derivative. And let me just write down the derivative like that. And this is basically, this derivative is what starts alien calculus, which will come back. Alien as not in the sense of alien invasion, but in the French sense of the word, dérivation étrangère. So more, I mean, I don't know who did this translation, but maybe it could have been called foreigner calculus instead of alien calculus. this again by Ekal in the 80s. And we will see that once we sort of start formalizing everything in terms of these derivations and these calculus, things also become extremely simple. Okay. So what would be, so I'm not sure, I think maybe one of the organizers can help me on this. There was supposed to be a break at some stage, and I'm not sure.
Yeah, that's exactly. I'm not sure whether we. I have the impression we didn't announce it. So in principle, you can take a break around after 1 hour, whenever it's fit. Whenever it's
as you guys want. So I mean, you know, if you don't shut me up, I will just keep going. So, just so please tell me when should I take a break, and I will of course stop.
So when it's about 1 hour after you start.
So within 10 minutes.
You find it's a good place to stop the lecture and take a break. It's completely up to you. I think because we started late, you started a bit less than an hour ago.
So okay, then let me talk for another couple of minutes, and then we take a break before exactly we start the example. So let me just take a couple.
Okay, sounds great.
Okay, sorry about that. Anyways, so let's just recap what we're trying to do. We're computing this observable, and we're looking at the perturbative expansion. Doesn't work. It's got 0 radius of convergence. And then Borel says, don't worry, just do a Borel transform. We kill the factorial growth. We're left with exponential growth, which means that I can compute this guy because its singularity is not, its first singularity is not close to the origin. You could say, what if it doesn't have singularities, by the way? What if it's an entire function? That doesn't happen except in trivial cases. So for the Borel transform to be entire, that would mean that there was no factorial growth to start off with. So whenever there's factorial growth, it's not entire. So there's always singularities. Let's say that singularity is there. We're not very happy with that one, but everywhere else is fine. So we just analytic continuing, and we Borel resum.
Can I ask a question? Sorry.
Yeah, please. At any stage, ask a question.
Thanks. What happens if we have a series that diverges worse than factorially?
I will tell you. Yes, so I'll tell you a little bit about it, hopefully still today or not. But then there's, of course, other more general Borel transforms that you could look at. In fact, most of the problems we will be interested in, it's not that they grow factorially fast, but they grow as some integer times g factorially fast. Is there anything wrong with? Did you see what I just wrote?
No, we didn't.
Because my screen's, I'm sorry, I think I'm going to stop share and reshare. My screen is frozen. Give me just 1 second, I'm sorry. This was...
Sure.
It stopped for a second. Hopefully it will come back now. Okay, now you see what I wrote, right?
Yeah.
Which was that. So I'm not even sure if when I did the recap, what I was talking about in the recap. Sorry about that. So it's not even the case that the growth of perturbation theory goes as g factorial, but it goes, well, in string theory problems goes as 2g factorial, or it could go as another integer factorial. So I mean, of course, we'll discuss all this more generic stuff. And it could be higher than factorial. There's a classification due to Gevret that I will hopefully come back to still today. Okay. And then you have to have this index M, Borel transforms and so on. This is something that at least, well, I mean, I have a very pragmatic attitude in these things in which I'm basically interested in the problems that I am trying to solve. And in the problems that I'm trying to solve, these higher Gevret cases have not appeared, so I will probably not have a lot to say about that. But I will go to that. Yeah. Any other questions?
Understood.
Okay, let's just in case. Okay, now just in case my screen was not working, we're looking at this observable. Its perturbative series doesn't help because of the factorial growth. Borel says kill the factorial growth and just do analytic continuation anywhere. There's always going to be singularities. I already said that in order for Borel to be entire, you really needed to start off with something which was much easier than factorial growth. So we just avoid the singularities. We Borel resum everywhere, and Stokes lines, we need to deal with them separately. And Stokes automorphism will come in a few minutes to the rescue to tell us how to do all these jumps. All right, so the question is, when I am crossing the Stokes line, something new is going to come into play, which is the singularity. And the way the singularity is going to translate at this level is into something which is known as creating something which is known as a trans-series, which is the generic solution to our problem. So I'm computing phi of x, put it this way. And I found that, well, I tried to start with the perturbative ansatz, which looks something like that, right? And that was not enough. So it turns out that I need to include more people. And sorry, that's not the G. And this is what I will call the trans-series. And not 0, because I already put the perturbative out. So let's start at 1. And I will tell you what these things are in a second. So sigma here, so this is just, of course, my perturbation theory, perturbative series. This guy here, I will call the trans-series parameter. And we will see in an example next that this basically is encoding boundary conditions of a problem. Or if it's an integral you're trying to solve, it encodes the choice of integration contours. It's sort of an external input that you have to put in. And these other guys here, these are basically, if you want, the n instanton contribution. So, and I'm, of course, obviously, there's a 0 there for perturbative and n there that we've already seen for instanton. And these guys have terms of this form. So the first thing you can see is that there's an instanton action there. This column might not be very good. And the second thing you can see is that these guys are basically transmonomials in the sense that because it's an exponential minus 1 over x, I really cannot do a power series expansion of this object at the origin. And then, of course, there could be perturbation theory around the nth instanton sector. So there will be coefficients that look like that. These are the G loops around the n instanton. And sometimes there's some factors that appear here. These beta n's are just some characteristic exponents that appear. And those are components that appear.
So just a quick question about, so the definition of a transmonomial is this?
So a transmonomial, we'll come back to that later on. But for the moment, a transmonomial is something which does not have a power series expansion. So for example, exponential of minus 1 over x at the origin, or exponential of minus x at infinity, or log of x at the origin, of log x, and so on.
I see. Okay, so any okay, very good. Thanks. So that's the definition.
Yeah. So basically something that I cannot write as a sum of phenomenon. But anyway.
That's a question. I have a question.
Yes.
May I? At the end of the day, we want to compute this function on left-hand side for arbitrary values of x.
Yes.
So if the series was Borel summable,
yes,
those different tricks you could play to find this function exactly. What I mean exactly, for any value of x, the possibility to compute the function with arbitrary accuracy. My question is, what you're expecting from this trans series if I want to be practical to computing this function for any value of x? You want to compute it exactly or with some accuracy?
So let's go back here to the Borel resummation, right? So you're saying, what if I do this one that I highlighted in red? There is no singularity, I'm good to go. Yes, I'm good to go. But this is going to tell me what's going on, you see, because there's a theta here, there's a path of integration here, and this S, which is following that path of integration, of course, relates to the argument of x in a very specific way. So whenever I do this integral here, I am computing x, I'm computing an array, which also implies, in this case, that basically the argument is inverted or whatever it is. So I'm looking along a specific array in x. And then you say, but I want to know this function as a function of x complex. Then I have to really look at every possible ray. And when I'm looking at every possible ray, well, there's going to be one ray which will have a problem.
My question is slightly different. I want to compute function. I don't want to know which technique you're using to compute it. I just have phi of x. I want to compute phi of x for given value of x with no ambiguity involved. What you just said, depending on which array I'm choosing, I'm getting different answer, which means there is some intrinsic ambiguity in the way how you use Borel transformation choosing the particular array. But I want to find the function which is an ambiguous number.
This is the, but hang on. Whenever you do this, this is an ambiguous number. This is the correct answer. This is the correct answer. This is the correct
answer. Answer is different, no? Depending on which direction you choose integrating.
Well, but look, if I compute the function at 1 or at I, the value is different, right? What I'm telling you is that as you vary x over the complex plane, you need to go back and trace how you computed it by Borel resummation.
Yes, but what you said, theta plus and theta minus, if I integrating slightly above and below the stop line,
yes,
we agree that you get different number.
Yes, but they are, that's the thing, that they're related by the Stokes automorphism. And so what you will see, and I mean, hopefully in one of the later lectures, I can show you how
to No, I don't want to take time.
Sorry. What we will see in some later lectures is that, you know, the difference of this junk can be highly exponentially suppressed. And so what you actually see is that, let's go to the trend series, is that there could be cases where, let's imagine this sigma was set to 0. And the computation of my function on the left-hand side here in yellow, it just involves the Borel resummation of the first yellow piece, nothing else. And I match, for some reason, I have a non-perturbative black box, which gives me the exact number, and I match it and say, it's the exact number. Then I say, okay, that's fine for a specific value of x. But then I start rotating around the complex plane, following x around, I don't know, some loop trajectory. And this guy will be good until this guy, all of it, will be good until there's going to be a Stokes line. And at the Stokes line, this guy turns on. And so after I cross the Stokes line, if I were just to sum this guy, my black box would say, no, it's not correct. So I really need to include this guy as well. And then the black box says, yes, you're right now. So not necessarily, this is Stokes phenomenon, right? Not necessarily the perturbative series.
No, I understood this, but this I perfectly understood. But my question is slightly different. In this second term, is the one with the Stokes line, the sigma term. So sum goes from 1 to infinity. So what I want to say is that if you want to get number exactly, you have to sum over infinite number of instantons.
Yes.
And it's not feasible.
No, that's not true. In some cases, you can actually do the complete multi-instantons sum. This is a procedure known as transymptotics that tells you how to do the sum over all instantons at each step in perturbation theory. This is actually, turns out to be something very nice. I don't know if I'll have time to get there. Certainly not today. It's something very nice where you can do all these sums exactly.
Thank you.
Sure, you're welcome. Okay, so let's try to recap again what we're trying to do. So we're trying to, we have an observable, we have a perturbation theory which is bad because of factorial growth, and Borel tells us kill the factorial growth so that you can do Borel resummation. And once you can do Borel resummation, you're in business, except at Stokes lines. And what basically this difference between the left and the right resummation is telling us is that you actually need to look not only at the perturbative object, but also at its non-perturbative completion in the trans series with multi-instanton sectors. And that introduces a trans series parameter, which is that guy there, which basically either is telling you about boundary conditions, for example, or initial conditions if you're doing a differential equation, or it's telling you about integration if you're doing an integral calculation of, I don't know, partition function, whatever, some sort. All right, so this is the objects that you need to include, and in fact, very much along the question I was just asked. So what at this level of the trans series, what's going to happen with Stokes phenomenon is the following: is that this relation that tells me that, and let's assume that theta is a Stokes line, and what we will see in the example, let me actually start by writing that. In this trans series that I wrote here, assuming that A is real, then the Stokes line, it's going to be, well, we'll see this very, very carefully in the example I'll show in the next hour. This Stokes line is along theta equal to 0. And so this means that I will have to consider Stokes phenomenon along 0, and what's going to happen. So I just dropped the 0. So what's going to happen at the level of the trans series is the following. Oops, that's next. And I will see immediately Stokes phenomenon. All right, so this can be very concretely done. As I said, I'm trying to do a time model. I'll stop in a minute. So this can be very concretely done in trying to compute this integral. I mean, this integral can be exactly computed. This is just a time model so that we illustrate. This 2 pi is just convention. To be honest, I no longer remember why we chose this convention. Okay, so this looks like a standard one-dimensional integral that you can do, in calculus 101 or as a toy model for statistical mechanics, quantum mechanics, field theory, whatever you want, where V is a quartic potential. All right, and so gamma is an integration contour. Let me stop sharing and let me share something else, if I can find it. So here's a notebook which has many of the examples that we've worked out here in the physics reports. They were carefully done. So I have to say that my coding skills are very bad. So, but happily my student, Roberto Vega, was kind enough to, because he codes very well, he was kind enough to write something a little bit more decent that I could present to an audience. And so there's many examples worked out here, and I will, show you a couple from time to time. And I would strongly suggest that you try to run some. I mean, at least the students try to run some of this in Mathematica. And by all means, write to Roberto, and he'll be happy to help you out with coding if that's an issue. And here what I'm doing is looking at the regions of integration. So I hope you can see my cursor. And so for the integral that I was showing you to converge, so this is so the color code is basically yellow/brown, which this is a color code from Marco Bertolla that calls this. I think it's a nice analogy: sand or continents, and blue is the water, and you have to choose your contours so that you don't get wet. So I like his analogy. So let me follow it. And so I have to start in some region on one of these 4 corners and end at some other region in one of those 4 corners, and I don't want to end up wet. And here's another view of that very same thing. So when we're doing, it's this Quartic. So let's go back to the iPad. Where's the button? Here we are. So that's what I've just showed you. That picture tells us about gamma and what are the admissible integration contours. And so what we'd like to do is compute this integral using sort of these ideas that I've been describing in the last hour, but I guess we will do that in the following hour. So as the request for the organizers, now we have a break, but I guess one of the organizers will have to tell us for how long the break is.
Yes. So the break will be for 15 minutes sharp, but before the break, I just wanted to ask whether there are any questions.
Please go ahead. Any questions at any time?
Okay, so if there are no questions, then we're going to have a break for 15 minutes sharp. So it's 11:17 according to my clock. So that's going to be at 11:32. Please, everybody, be back because we're going to start the.
Monica, if I may, I will leave my Zoom open. So if anybody has any questions in this 15-minute break, please just come to Zoom and tell me. I'm here.
That's very kind.
Sure.
Ricardo, it's me, Josip Bena. Sorry, I mean, I didn't want to ask. I just had a question about. I mean, I missed. Unfortunately, I had to hang up for a while, so I missed this thing about the Stokes line. So the point is never. So when you discuss about the Stokes line, so essentially there's a Borel resummation which works on one part of the contour and then it works on the other side, and basically the answers are not the same, right? And this is the Stokes line.
Mm-hmm. That's right. So when there's a singularity, you can't define the Laplace integral, right?
Mm-hmm.
So then you're done. So what you do is you define the Laplace integral just before the singularity. You define the Laplace integral just after the singularity. And the magic of the beauty of this is that they're actually related to one another by these Stokes counts.
Mm-hmm. I see. Okay, thanks.
Sure.
May I continue my question?
Sure.
So we agree that the fact that you have Borel singularity is one-to-one correspondence to the fact that you have functions which have certain singularities, and you're basically explaining the function around singularity.
Mm-hmm.
So, which means that if I knew from the very beginning, just less tons of logic around, if I knew everything about analytical properties of my function, I would be able just to write a Cauchy integral representation expressing my function for any values of x, like contour integral in the region when it's analytical.
Yeah, but now you're talking about, so when you know all the singularities of your function, you mean all the singularities of the Borel transform.
No. Forget about Borel transform.
Okay.
I'm just asking general question. The Borel transform is just a tool which allows you to understand certain property of function. But what I'm saying is that let's think about where those Borel singularity came from. What's the origin of those n-factorial behavior of perturbative expansion? And what I'm saying is this n-factorial behavior appears to the fact you're dealing with some function whose analytical properties you don't know. And the fact that you found n-factorial behavior, it signals you that you're talking about expanding your function at the point when it has singularity.
So so the issue is that basically you're always expanding the original function you're starting off with as if you're sitting next to a branch cut.
Exactly. So therefore, if somebody would told me in advance what analytical properties of my function, position of the branch cut, what kind of discontinuity the function has, I would be able just to write Cauchy representation and compute the function just exactly for any value.
Sure, but that's something else. That's not what we're doing, right?
Agreed.
Okay.
So what you're doing is basically you have a function whose analytical properties you don't know a priori, and you're trying to use Borel singularities together with Stokes line phenomena to reconstruct those information that you're missing to start with. So therefore, my question is that somehow you know that you're dealing with a function which has certain complicated analytical structure, and what you're trying to do, you're trying kind of to reconstruct using this technique that you're describing, position of singularities, the nature of singularity, etc., etc., etc. And then my question is basically a question which I asked you previously: is that how do you know that this information, by the singularity, Stokes phenomena, etc., etc., will allow you to reconstruct unambiguously this information? Another way, is it possible to have two different functions which have the same structure of perturbative expansion with the same position of Stokes lines, with the same jumps across the Stokes lines?
Well, if everything is the same, then there's no ambiguity, right? This is what I was saying. I mean, you can have different functions that have similar structure. I don't know, they have just a one parameter transeries, whatever. These, of course, you can have millions of them. But if everything is the same, including Stokes data and so on, then you're unambiguously constructing your function. I mean, there's theorems about this. I'm not going to go into theorems, but I think in the audience, I'm not sure if he left already, but David Sazan was here and he proved many theorems on these issues that you can also talk to him about. But let me just add one more thing. Let me just add one more thing, which is that it's not only that this Borel transforms and all this method is interesting as sort of a mathematical toolkit to construct your function, that it's giving you a little bit else, which is it's giving you a semi-classical decoding of non-perturbative phenomenon, because it tells you about instantons, it tells you about phenomenons, it tells you about D-branes. So it's also giving you physical information about what sort of semi-classical non-perturbative objects you have around. So I think it's not only about being a mathematical toolkit, but it's also a physical insight into semi-classical decodings of non-perturbative.
No, this I understood, but I understood the general philosophy. But as I said, in the practical terms, for example, just to be more concrete, you go to like QCD, don't talk about a normal one.
Well, I mean, that's a harder problem.
Okay, very good. And then, so you're dealing with those non-perturbative corrections which appear through the normal on perturbative expansion.
Yeah.
But first of all, nobody succeeded to perform the resummation up to the point that you kind of could compute a physical quantity non-perturbatively in QCD, knowing information about perturbative expansion only.
No, not in QCD. So, but you have some Monte Carlo results looking at large order by.
No, but what
yes,
I meant something else.
Okay.
Then in QCD, you have two different kinds of perturbative phenomena entering. Those which could be seen at the level of perturbative expansion through normal ones.
Yes.
But there is also non-perturbative corrections, which are not seen through factorial divergence of perturbative expansion.
Yes.
There is intrinsically non-perturbative phenomena which cannot be spotted by looking for the perturbative expansions. And that's what I mean, that there is certain information which are missing as soon as you're dealing with perturbative expansion only.
What would perturbation theory not see? What are you talking about now?
For example, chiral condensate. You have certain symmetries which are exact in perturbative expansion, but those symmetries are broken only at the level of non-perturbative physics.
Yes. Okay. So I mean, look, you're picking an example where it's particularly hard because people have gone to 20 loops using Monte Carlo alone. So I mean, I don't want to be very definite on what's happened. What I can be definite about is on examples where we have managed to go deep into the perturbative large order, and there we're definitely not missing anything. I mean, this can be checked. I will talk about a little bit about.
No. I understood. Basically, the logic is if there is some non-perturbative physics which has any imprints in perturbative expansion, this technique which you're explaining allows you to capture them exactly.
Yeah.
This I understood.
Yeah.
But simply, what I want to say is that at face value, I would say a bit stronger statement that having perturbative information only allows you to reconstruct the quantity non-perturbatively.
Can I intervene a little bit?
Yes, please.
Yeah. So what can be said is that the fact that the perturbative, the large order behavior of perturbative series, which is extremely hard to capture, by the way, can tell you something about the non-perturbative part, relies on an hypothesis, or that can sometimes be proved or not, that the series is resurgent. On proving that something is resurgent is really hard. One question is, for example, QCD or everything, are they resurgent or not?
Yeah.
And I don't know if there is a definite answer to that at the moment. I don't know if there is anything proved. And somehow it's an hypothesis that we are making that all interesting physical theories should be resurgent. Is that true?
I think, Bertrand, for QCD, the answer is definitely no. As I just said, there is certain phenomena which are not seen at the level of classical physics. You have you start from the classical Lagrangian, which has certain symmetries.
Mm.
But then you know that those symmetries are broken non-perturbatively.
Mm.
And if you have symmetries broken non-perturbatively, like kind of the anomaly which is not seen at the level of perturbative expansion, to any of the perturbative expansion, you have some current which is conserved. Simply, it's zero to any of the uncoupling constant. But if you measure it non-perturbatively on the lattice, whatever, it's different from zero. Physics is such that it's different from zero. So therefore, perturbation theory will never ever predict you these objects to be non-conserved.
Well, I think that resurgent theory methods can allow to compute these kind of things and can give answers to that, but it depends on I don't know if your theory is resurgent or not.
Yes, I think Bertrand is making a fair point. And I mean, let me be agnostic on this because I have not looked carefully at the example that Ricardo is saying. But we have never met a function yet that was not resurgent in any of the examples we're looking at. I mean, I'm not saying that we will never do so, but so far we have not. But maybe David Sozan wants to say something about this.
No, I have no.
Oh, I thought you were turned on because you could make a comment about at least about the generality of how many functions are actually resurgent out there.
Well, I could give you just a simple question. So let's go to some confining C like QCD. So you're talking mass of the pion.
Mm-hmm. So
would you expect that you could compute mass of the pion by resurgent methods?
Look, I mean, you're asking me, can you quantize gravity? I don't know. I mean,
no, but let's be very concrete. Nobody knows about gravity, but pion particles which exist in nature, and it's mass, right? It's physical number, it's number.
Yes.
My claim is that this number is non-perturbative in a sense. It cannot be computed by any resurgent method whatsoever to any perturbative expansion in G square, because this mass of the pion appears through this chiral symmetry breaking with phenomena which is not seen to any of the perturbative expansion because of the chiral symmetry of QCD and for master squark.
Yeah.
I don't want to to take too much time. Just simply make my statement and shut up.
No, I mean, I understand your point. What I'm saying is that, I mean, again, I have not tried to work out the example you're saying. So I don't want to start saying things which are completely wrong or whatever.
Yeah.
But I can tell you about examples that we've looked at, and we can actually see that, non-perturbative phenomenon being that we can compare against things where, again, we have a black box that tells us what the exact results are. And we can always do all these maps. I mean, we can see how perturbation theory stops sort of making sense and matching against what the black box says. But the train theories itself knows about what's going on and is telling you exactly what's going on.
Would you agree on the following formulations? That basically what you're saying is that you have instantons, whatever. So you're computing a quantity, and you know from the very beginning the exact path integral for this quantity is saturated by certain classical configuration, let it be trivial vacuum, instanton, etc., etc.
Yeah.
So therefore, as soon as you know that your quantity is exact in the sense that it's given by the saddle points coming from the solution to the classical equation in motion, then your method is perfectly will be exact. But if you knew that the vacuum of your theory is not saturated by instanton, then you're missing something.
Well, yes, then you're missing whatever saddle points there are. So, I mean, if your question is, can we give a semi-classical description of renormalons? I agree that we're far from that, but, I cannot say that once we had a semi-classical description of renormalons, I'm no longer sure that your claim would hold. But again, it's a problem I've not tried to work out, so I don't want to be.
No, but I think I would agree on the statement that you just said, that if you knew that your kind of vacuum, your theory is kind of gas built of the instantons, God knows what, but those feature classical solution to the equation of motion, then this technique is perfectly applicable and you'll get exact answers. But if you knew that vacuum is more complicated, and this is the case in QCD, we don't know really, yet.
Sure.
Then you something unknown, and then the question is open.
Yes.
I mean,
Jean, please.
Obviously, QCD. I mean, the ECAL theory, the theory of resurgence, is based on partial differential equations, and not on functional integrals and functional equations. And for what concerns QCD, since we don't even know that QCD does exist, there is no math. There is $1 million price to prove that the existence of QCD. Okay, we can certainly not assert that QCD can be dealt with by the method, semi-classical method, or resurgence theory.
So I totally agree that, I mean, we certainly have the theorems that we have, and David Sozan can tell us more about it, but the theorems we have are, I don't think they're even for partial differential equations, they're for nonlinear ordinary differential equations and for nonlinear finite difference equations. So when it concerns the theorems, I completely agree with that. Now, there's many other examples, which are not QCD, but in string theory and so on, where we're also not dealing with differential equations. And there we have managed to check that the functions that we're computing are resurgent. So that's why I'm saying that I would at this stage, I would be completely agnostic about QCD. I mean, I wouldn't pick a side.
Well, I can just say that typically in some supersymmetric string theories, typically topological and so on, we can go very far in this process, and we can indeed extract the non-perturbative information from the perturbative one. And in these cases, we have many examples where we know that it works.
Yes.
Bertrand, but in those series, vacuum is, as I said, is kind of trivial in the sense that, okay, it's not trivial, but it's trivial in the sense that you know that it's saturated by those instanton configurations. Non-trivial solution to classical equation of motion.
Well, no, we don't take that as a first principle. We find that as a result somehow from the perturbative theory.
True, but do you believe, let's once again, do you believe that the vacuum in those topological theories it's kind of saturated by classical configurations? There is nothing beyond classical solutions equation.
No, I'm not sure of that. Huh? I mean, no, I'm not sure of that.
Sorry to interrupt this interesting discussion. So I think we should end the break if Ricardo is ready for part 2.
Is it time to end the break, Monica? When
Yes, did people not hear me?
I don't know. I was in the kitchen. Sorry.
Okay. Yes. So if you're ready, we can already start
Sorry
with,
about that.
with part two. And just about the end. So I mean, part two is also about an hour, but if you need a little bit more, there's no just.
That's fine. I mean, there's several lectures, so let's not go over time at all. Yes.
So, but it's completely up to you. Whenever it's a good time to stop, in about an hour, it's a good time to stop.
Yeah.
Yes.
Let's keep the schedule. Okay. All right. So let's restart. So let me go back to my iPad. Okay. So can we compute this Quartic integral? Well, the answer is obviously yes. Let's see how. Let me illustrate with the notebook, maybe. So we go slightly faster now for a minute. All right. So we're looking at this Quartic integral. And I'm assuming this is recorded. So, you can always come back and look at the screen just to get some pointers on how to write the code to make this, these numerical experiences, explorations, whatever you want to call them.
By the way, there was a question in the chat whether you could make this, it's possible to make this Mathematica notebook available, maybe in the...
Sure. I think Roberto will be, I'll double check with Roberto. I think he'll be okay with it. So I can check.
Okay, thanks.
Then I'll send it to you, whatever, and you can check. So here we're again, as I said, I hope you can see my cursor. I don't have another option here now. So we're trying to find contours of integration that go from land to land and not to the ocean, so we don't get wet. So here's just another way to look at it. And so how would you compute the integral? So the first thing we would do would compute saddle points of the integral. So here's, this is, again, Roberto did a really nice job in making the code very pedagogical, explaining what each function is doing at each stage, so that if you guys want to play with it, it's easy to follow it. And so here we have our Quartic potential that I had written in the iPad before. And here is a function that's just computing minima for you. It's basically looking at zeros of the derivative, right? It's a trivial. And we find that we have basically 3 saddle points. So 0, we will call the perturbative saddle point of the perturbative expansion. And then we have plus and minus square root of 6/6, which we will call non-perturbative or instanton saddle points, or whatever you want. And then we would like to do some saddle point integration to do the analysis. So here the code is a little bit more intricate. So I will certainly not go through it, also because, as I've already said, my coding skills are very low. But we're just basically plotting, again, the colors are slightly different, but you can see there's land and there's the ocean. And I'm plotting the steepest descent contour. So here's the saddle, that's the perturbative saddle. So here you're seeing that, I'll come to this formula in a second. That's the, let's call it the plus instanton saddle, and that's in red, let's call it the minus instanton saddle. And so what Mathematica is doing here, it's plotting both steepest descent and steepest ascent contours. And so you can tell the difference because, so let's just look at this. I'll go to the iPad in a second. Let's just look at the plots for a second first. You can see that here I started off in land. I go through the perturbative saddle and I end up in land. So that's the steepest descent contour for my integral. This one, which is also plotted, is of course, I start out in the water and end in the water. So it's the steepest ascent contour. So, I mean, if you want, again, I asked Roberto to do this in an afternoon. So of course, this is not highly sophisticated, but if you want, here's something that you can try to do more sophisticated, is ask Mathematica not to plot steepest ascent contours, just steepest descent contours. And here's our, and in black solid, the contours are saying that they're dominant. So I mean, the dominant contribution is this contour here that I'm going through with the cursor. Then there's subdominant contours, which goes through the instanton saddle. They're dashed, and the dashed means that, yes, is there a question? No. And the dashed means that they're subleading. So later on, you will see that it's going to be the perturbatives that are going to be subleading, and it's going to be the non-perturbatives which are leading, but we'll come back to that in a minute. Which plot was I showing? The second plot. And the dashed ones, you see here a steepest descent contour. It goes from land to land, and you see there a steepest ascent contour goes from the water to the water. So again, just on this region, let's just think about steepest descents. All right, let's go back to the iPad. So I write a formula just to tell you exactly what we're plotting there. Where's the iPad? Okay. Here we go. All right, so saddle points, just a quick word, we're ready. I think it's got one L too much. Are these ones, we just computed them in Mathematica. And this means that the leading contribution to the integral, which is of the form, is going to be 1 or this. Okay, it's just plugging back in. So I think I'm doing absolutely straightforward stuff. And so the next thing you would want is steepest descent. And that's what was plotted in the notebook of Roberto. And it's basically, let me not put 0 because it could be actually any of the saddles. And that's what you're looking for, okay? And you go and you do these plots. So let's go back to Mathematica and see what's going on with the plots. Of course, in person, this would be much faster because Mathematica would be up in the screen and I wouldn't have to be switching between the screen and the blackboard, but anyways. So we see here, and now we start moving around a loop in X. And we see that, well, the perturbative saddle is dominating and the non-perturbative saddles just give exponentially suppressed contributions. So here, is it written here? I hope so. So X is, remember, the quartic coupling over there. And I am rotating the quartic coupling for different angles as written here. Okay, exponential of I theta. So I'm rotating the quartic. And I start, and here is always telling me up here in the plot, you see there's a 0 there, there's a pi over 16 there. It's always telling me at which argument I'm looking at for the quartic coupling. So basically the absolute value is 1, and I'm just looking at theta. And so here we start off with what's the usual contribution. Then I start going to pi over 16. That's the leading steepest descent guy. I keep going, that's the steepest descent guy. And then at pi over 2, something funny happens, which is that at pi over 2, I am basically on an anti-Stokes line. Everybody, I should have said that, yeah, in fact, I'm sorry, to be fully rigorous, I should have said that at 0 already something funny happens, which is that the steepest descent contour goes through all the saddles, right? So in fact, imagine backing up from pi 16 to 0, and you see this is the steepest descent contour that only goes through the perturbative saddle. And as I back up to 0, it touches all saddles. So that's a Stokes line. So I should have started there with the Stokes line. And so that line says, okay, these guys are exponentially suppressed, but I've seen them by the steepest descent integration, or by the steepest descent contour, to be more precise. And so when we reach pi over 2, another funny thing happens, which is that everybody has the same weight. And we plot this here in the figure by the dashed contours, which were exponentially suppressed at 7 pi over 16, with comparison to the solid contours, they now are all solid, which means, okay, everybody has the same weight. And that's an anti-Stokes law. So at the anti-Stokes, the instantons have the same weight as the perturbative component. And then as I move forward, things change. Now, as I move forward, it's, yes? Somebody is talking. I'm not sure if one of the organizers can mute whoever's talking. Thank you. And then once I've passed my anti-Stokes line, the leading people are now the instantons. You can see that because now they're the solid ones. And the perturbative guy is now subleading because, this is still order 1, but the exponentials are now, instead of suppressed, are enhanced. So order 1 compared to an enhanced exponential is, of course, exponentially suppressed. And so these guys take over, and they keep taking over until we reach pi. At pi, I have another Stokes line. You see the integration contours, they all touch all saddles, so everybody sees everybody. Remember that you could say, but the instantons are on water. Yes, because there was a sign change, but we kept the color coding of the background. So now I should be going from water to water. And then the Stokes line, so in some sense, if I was at 15 pi over 16, and I would only be looking at leading contributions, I would only see instantons, I would not see the perturbative contribution. But then pi is again a Stokes line and says, oh, look, the perturbative guy was there. Let's take it along for the ride. Might become important later on. So I keep going. The instantons are still dominant until I reach 3 pi over 2. Everybody is again the same weight. They're all solid. So they're all order 1. And things came back to normal afterwards. So again, it's basically the perturbative which is leading, and the instant, by normal, I mean, according to our classical, semi-classical convention. The perturbative is already leading, and the instantons are suppressed. And we come back to the same. Okay. All right. So that's a neat, very simple example. But as I said, today would be it's a boring lecture for all senior people. This is really just to make sure that everybody is on board. And in fact, one thing I'm trying to do is that even undergraduates can follow this. Okay, let's. Oh, I'm sorry. I went back to sharing mathematics. I pressed the wrong button. I apologize. I wanted to share the iPad. Where's the iPad? There it is. Okay, so now it should work. Okay, we're back to the iPad. All right, so just to make precise the plots I've said, I mean, I can just say 2 things now. One is that Stokes lines, let's just write that, are at argument of x equals 0 and pi. And so, which you could write imaginary part of, so the instantons and the perturbative, the saddle, the steepest descent contours, they touch both saddles. So that's just basically the requirement. This translates to the imaginary part of 1 over x is equal to 0. And voila, that's the answer. The anti-Stokes lines, the anti-Stokes lines, we saw them at arc of x equals pi over 2 and 3 pi over 2. And so we want everybody to have the same weight. So instead of looking at the real part, instead of looking at the imaginary part, we look at the real part. So we're saying that the weight of the instantons is the same as the weight of the perturbative. And this translates to the real part of 1 over x is equal to 0, or that's the answer. So that's it. So here's an ultra simple example where we can do the calculation, basically a plot. Any question on that? All right, now you could say, yeah, that's very nice, but I mean, I actually had a class on steepest descent contours, so I mean, this is not really a novelty. And you were telling about how all these perturbative series, I want to look at their large order and so on and so forth. So what else could I do that goes more into what you were telling us about earlier? So let's ask about the full perturbative content. and maybe I should be a bit more precise, also the full non-perturbative content of this quartic integral. So it turns out that, and you know, homework derives this. It turns out that that quartic integral actually satisfies a linear ODE. I mean, this is really the simplest possible example that looks physically motivated that I could come up with. So this is second order linear ODE. And so if I know the solutions to the second order linear ODE, I know the solution to my quartic integral. So I should be able to reproduce everything that I've just illustrated easily. So let's do this in the flavor of what we discussed earlier. So I'm using an ansatz where I'm going to assume that this guy could have transmonomials, A over X, times some power series. So this is transmonomial, and this is power series. And if you just use these ansatz and put it back into that differential equation up there, you find that there's two options for A, 0 and 3/2. You say, okay, good. So I sort of found my instanton action. And yeah, that matches what we just computed from the integral. So that looks reasonable. And 1, remember? So, okay. But can I do more? Because now I can actually start plugging in and computing all these perturbative coefficients. And the answer, of course, is yes, you can do it. And I'm not going to do it for you. But again, I suggest the students should try to do this. And you find that there's a power series associated to the 0 instanton action, which looks like this, where these coefficients are, I'm sorry, I need my glasses, I can't read what's written here. They're 2 over 3 to the power n, or n factorial. Let me actually write them all down because they're quite illustrative of what's going on. Times some number. This number is at the moment unspecified. I will tell you how to fix it in a second. And then phi1 is similar. And it looks like that. And okay, I will have to use this too. And then the rest is just basically the same. And then there's a number there. So the first thing you see, or well, I don't know if it's the first, but one thing you see is that you have instanton action here. Well, 1 over the instanton action. So you see that, let me try to have everything on screen. You see that ZNs, either 0 or 1, it doesn't really matter. They go as 1 over the instanton action to the power n. Remember that the instanton action was 3/2. And then you see, okay, that's interesting. We've already seen that. And then, okay, let me do just some hand waving. I have 4, 2, 1. So I sort of kill the 2, kill the 1, kill the 4. So super hand waving, but n factorial. And you say, ah, this is exactly what I expected to find. So I do have my n factorial leading rows, and I do have my next to leading rows controlled by an exponential growing term, which is the instanton action. Ah, that's very nice. Okay, that looks good. Then, well, I don't think this is very relevant. It turns out that you can fix these constants by just looking at integration contours, but it doesn't really matter for the sake of what I want to say next. So let's just assume that they've been computing. They give factors of I over square root of 2, so whatever it is. Next thing, I can also, by just looking at, I should have said something before, I'm sorry. I think I gave one step too fast. Where is that formula? Is that, let me write the things again properly. So now I can say that my differential equation has a perturbative sector, which is, okay, let me write down the formula. Looks like that. So I already fixed that coefficient. let me actually write this, guys. And the other one, this is also the coefficient which has been fixed, is this one. And the coefficients, I'm not listing them because I've already listed them for you. And then you can see, the next thing you can see is, okay, so I have the transmonomial there. And here I have just monomials, and here I have just monomials. Okay, it's looking good. Stokes and anti-Stokes lines can be found, again, it's exactly the same formula as before, by just looking at the instanton contribution up there. So I know that Stokes are going to be associated to the imaginary part of that term being equal to 0. Yes, we've seen that before. And anti-Stokes, yeah, a little bit of space, is the real part of that guy being equal to 0. Yes, we've seen that before, so everything is making sense. And now, and look, we're dealing with a second order linear ODE. So, I mean, I'm saying a complete triviality from the point of view of differential equations, which is what is the general solution to this differential equation? Well, it's second order. So the dimension of the space of solutions is bidimensional. So, I mean, if I have two independent solutions, which I do because of the transmonomial, then I just have to add them. So how would you do it if you were in, differential equations 101? Well, you just write immediately down the solution. And the solution, I'm going to denote it with a curly Z, depends on two integration constants. Let's call them sigma 0 and sigma 1. And it's sigma 0 times Z0 plus sigma 1 times Z1. And you say, well, that looks like the trans series. Yeah, it does look like a trans series. So I mean, again, from this point of view, it's a complete triviality. This is a trans series solution. And it is a trans series solution because there's a transmonomial. So this is really easy. Yeah, okay, no problem. Of course, once we go away, I mean, this has basically nothing to say for linear differential equations, right? I mean, again, I'm choosing the simplest possible example I could think of. Once we move to non-linear or even things that are not defined by differential equations, or the discussion of QCD that we're having in the break and so on, of course, these things get tremendously more complicated. But for the moment, let's just play with this simple example and let's try to illustrate everything that's going on. Okay, this looks good. That's my trans series solution. But the trans series solution, the components of the trans series solution are power series, even though there's a transmonomial there, but I mean, there is this power series, and this power series that I've just said, they're asymptotic, right? Maybe I should have written it there. Asymptotic. I'm sorry, sometimes I pick wrong colors, but anyways, it's because of the factorial growth. So I still need to Borel transform these people to get try to get something nice. All right, let's Borel transform these people. So when I Borel transform these guys, it's actually quite simple. You see, I have a factorial here, I have a factorial there, I have a factorial there. When I Borel transform, I'm going to get another factorial there. And of course, you all know about functions which are defined as power series, which have a factorial on top and 3 factorials on the bottom. They're just hypergeometric. So this calculation is actually also very simple. So if I do my Borel transform, what I'm going to find is the following. So the Borel of phi 0 is going to be this value here. I think, and I should have already done this, I'm sorry, I keep following the primer, the physics report primer, where we didn't fix h bar. In the notebook, h bar is just set to 2 pi so that many formulas simplify. Let me actually set h bar to 2 pi so I don't have to go with this guy around here. And here's the hypergeometric to F1. And Borel of phi 1 is also given by hypergeometric.
By the way, Ricardo, I don't know if I can't see what you're writing. I don't know if other.
Oh, I'm sorry. Yes, you're absolutely right. So let me stop share and reshare. This is some issue that happened already 1 minute ago. Please, if this happens, tell me immediately. Sometimes I'm just looking at the screen, and I didn't notice that the iPad stopped sharing for some reason.
It only stopped sharing after you erased the h bar over 2 pi. So it's
okay. So, well, anyways, I didn't write a lot, so it should be okay. So let me just review what I said. So I set h bar to 2 pi, and then I just said that sum that I had already pointed out for you before, it just gives you hypergeometric. That's the hypergeometric it gives. And then for the phi1 sector, that's what I was writing now, it gives you this, excuse me, gives you these other hypergeometric. All right, there we go. Say, okay, good. This looks nice. These functions are familiar. I mean, you can go to the NIST book, Handbook of Mathematical Functions, and you know everything you ever wanted to know, but were afraid to ask about hypergeometrics. And they have a branch cut at z equals to 1. So you see which, from this point of view, is s equals 3/2, and here is s equals -3/2. What was 3/2? Ah, wait, 3/2. I saw 3/2 earlier. Ah, there it is. 3/2 was the instanton action. Okay, oh, this seems to be very consistent. So great. And I have a branch cut. So you could ask, what's the nature of this branch cut? What happens to the Borel transform near that branch cut? And by the way, the fact that I have a branch cut, maybe I have a plot. We're totally in this situation that I'm plotting right here, where now this guy is, of course, 3/2 or -3/2. I have my Stokes line on the positive real axis or on my negative real axis. I have my singularity. So I can, see in a very simple example what's going on. Okay. Let's expand the Borel transform. So first of all, let me stop using 3/2. So this is going to be, sorry, that maybe I should wait the other way. This is going to be equal to A. It's going to be equal to -A. It's just what A is. And let's expand the Borel transforms next to their singularities. So I'm going to expand this guy near A. And I'm going to expand this guy near -A. What do they look like? All right, you can play a bit with mathematics if you want, or do it analytically. I mean, again, whatever you want to do. And here's what happens. So when I look at the Borel transform of phi naught, I get a number. Then I get a pool times the coefficient that I've seen before, plus, that's the same number, times, and now here things happen weird. There's the log, because it's a branch cut. It's not just a singularity, it's a log branch cut. And then let me just, if you don't mind, change the color here. And then what I find here, I find something that I will tell you in a second, plus holomorphic stuff. Okay, so I don't care about it. And then I find a bunch of stuff here in yellow, in dots. And then when I play a bit with that bunch of stuff that I find, it turns out that I can write it in a different way. I can write it like this. The Borel of phi1 expanded around A. Oh, that's interesting. And if you don't mind, let me also change the color of this guy here. It will be relevant in a minute. Say, interesting. What happens if I do the same for phi1? Well, I find the exact same structure if I do the same for phi1. I find a number. Now it's -1. Then I find a pool. I'm expanding now around -A, so that's a plus. And it's got a coefficient that I've seen before there on top. And then what else do I find? Trying to put everything in the same board. I find, oh, look, there's a number, which is the same I saw before. Then I find a log branch cut. Fix that -A, plus A. Yeah, no, I'm sorry, -A, yeah. 2 pi I. Then I find stuff. And then I find a holomorphic that I don't care. I'm just looking at the singular pieces. And okay, what can I do with that stuff? Well, I play a bit with it. And it turns out that this is the Borel at phi0 expanded around S plus A. And then you would say, ah, this is very neat, because what am I seeing? And now let's use the language. When I expand phi naught around its singularity, I find phi1 reappearing at the singularity. Or if you want to use the word that you're expecting, I'm finding the resurgence of phi1 next to that singularity. The same for phi1. When I expand the Borel of phi1 near its singularity, and the singularity is now located at minus A, I find the resurgence of the perturbative sector near that singularity. So that's the origin of the name resurgence. The non-perturbative sectors reappear, resurge at the singularities of the other sectors. And that's not the whole story, because of course, they reappear up to a proportionality factor. That proportionality factor, it's Stokes data, is the Stokes coefficient, or related to. Here, maybe one thing we could call it would be the Borel residue, the Stokes Borel residue. I will tell you why there's slightly different names, hopefully before the end of this lecture. You say, okay, so here we have resurgence at work. If all I knew was phi naught, I would compute its Borel transform. I would look what happens near its singularity, and I would find the resurgence of the non-perturbative sector. And vice versa. If all I knew was phi1, at its singularity, I would find the resurgence of the phi naught of the perturbative sector. That's resurgence in a blackboard. Can we be slightly, we don't want to be writing all these long Borel singularities with branch cuts and so on all the time. So can we be slightly more efficient? We can be slightly more efficient. So now let's write the exact same thing, trying to abstract information as much as possible. And the only really relevant information is that there's phi naught there, there's A there, and there's the resurgence of the non-perturbative sector up to the Stokes coefficient. And the same, there's phi1 there. Now it's around minus A, and there's the resurgence of the perturbative sector up to the Stokes coefficient. So let's rewrite this in a slightly different way. So let's compute this difference of Borel resummations on the sector phi naught. And if you do the calculation, this is what you find. And let's do the same around pi. So if I don't put anyone, it's because I just said the first one was 0, right? Okay, maybe I can put a 0 there if you feel better. And this is equal to +1. So the sign changes just because of the contours. They are there once you want to close the contour. You say, okay, now this is a slightly neater formula. Can I make an even slightly neater formula? Yes, I can define something. This is a bad definition, by the way, because it only works in this linear case. But so this is certainly not the general definition, but for the purpose, for pedagogical purposes, let's just work with this definition for a second. And I will call this object the alien derivative at omega. And then if you just, it's not too hard to see that, you just grab these exponentials, you plug them there. And so what I have on the left-hand side now is the alien derivative. So this is what I have. And this is all information that I need to play resurgence game. So this is what alien derivatives are. So they're no longer a very mysterious object because we can see how they appear very neatly in super simple context. They're just a way to encode the exact same information as up here. It's telling us that at the A singularity up to the Stokes coefficient, I see the resurgence of phi1. And for phi1, at its minus a singularity up to the Stokes coefficient, I'd see the resurgence of I0. Let's just jump quickly there. There we go. It's exactly the same information. And they're actually quite neat because, I mean, the structure is very simple. So if I represent my trans series as 2 blocks, and there's nobody else. These are the building blocks of the trans series for this ultra trivial example. Then I move from one block to the other with delta plus, and I come back with delta minus. That's all there is, nothing else. And any alien derivative anywhere else is 0. So, I mean, the reason, by the way, that this is called a derivative is because, of course, it satisfies Leibniz rule, but in this case, it's a triviality. I mean, there's almost nothing to say. And all this.
Ask a question.
Let me just say one more thing, and then please go. Let me just finish this. And all this up to Stokes data. And the Stokes data of this problem is S plus A is -2, and S minus A is 1. And we have everything. So please go ahead. There was a question. So.
Yes. So the Stokes data or the Stokes coefficients are always real, or in general are complex?
No.
Okay.
I mean, hopefully I'll come to point number 1 where they are transcendental. So they can be a horrendous mess in generic case. Of course, in linear examples, yes, they're always integers. There's many nice examples that have been recently worked out by Marcos Marinho, Stavros Garofalidis, and Gigu, where they've shown that many of them are rational. In some specific cases for topological strings and toric varieties, you get a bunch of rational Stokes data. But the more complicated stuff, such as point 1, which is just the beginning of a lot of minimal string theories, they all become transcendental, complex transcendental. So, I mean, we've managed to compute all of them, but it's pretty nasty.
I see.
So, look, I'm trying to illustrate this in the simplest possible example. Lots of things can go, more complicated very quickly. Hopefully, we'll get to there. But again, as I said today, the lecture is going to be elementary undergraduate as much as possible.
Thanks.
All right. What else? Okay, now we have alien derivatives, and we can start thinking, what about Stokes phenomenon? Is there a Stokes phenomenon in this example? Maybe. What we saw earlier, I told you, is that Stokes phenomenon So I apologize for being so elementary today, but I think it's better that all the students get on board before doing complicated stuff. So, I mean, sorry about that. Stokes phenomenon was sort of controlled by the Stokes automorphism. His weird object. It's math frac on LaTeX, if you want to know what is the source of this font. And it's basically written. So, I mean, I was supposing, my expectation for today was still to do the mathematical derivation of many of these things, which clearly is not going to happen. So, but these things will be very much derived on Monday. So, which is given by the exponential of the following object. So, for the moment, just carry with me. We will see that it all makes sense when I write down the formula on the example that we have at hand. And then on Monday, we will see where this formula comes from. So I have a derivative here. Well, to be honest, I didn't prove this was a derivative, but let's just assume that it satisfies Leibniz rule, which means that its exponential is an automorphism. So again, I didn't prove that, but we will see that we'll actually see in a second. And I'm just including these exponential factors in front of the alien derivative and summing over all singularities. And you could say, okay, that looks pretty horrible. But let's see what happens if I just apply this definition to the problem that I have at hand. Remember that something very simple happens, which is that there are no multiple alien derivatives, because if I act here with, on the same direction, if I act here with another plus, that would be a plus there, and that's it. The plus here would be equal to 0. Of course, if I act with a minus here, there's a minus there, it keeps going. But there's no multiple derivatives of the same kind. The same if I act with a minus here, that's a minus here, and that would be equal to 0. So all these exponentials, so the exponential is creating multiple alien derivatives along the same direction. I'm at fixed theta. These exponentials collapse. They're actually basically a triviality. Let's write them down. So let's compute that guy on phi naught. That's exponential of minus a over x delta plus on phi naught, which is basically phi naught. That's the one. Minus 2 exponential of minus 3 over 2x phi 1. Nobody else, because the next double derivative, double plus, is 0. Same thing for phi pi. And of course, if you act with the Stokes automorphism on phi 1, that's just 0. So you just act with Stokes automorphism at pi on phi 1, and you do the same calculation. Let me not do it, otherwise we never finish. We get that. Where just remember that the one there was a Stokes coefficient. Okay, so you see the Stokes coefficient there, which is a minus 2, but the other Stokes coefficient was actually 1, so it's still implicitly there. And you say, okay, that looks much neater than the grain formula. Can we make it even neater? Yeah, we can, because we can just write this for Z. Remember, let me just recall you what Z was, because Blackboard is not always here. If I can find it. Remember that the phi's are just the perturbative series. Well, the asymptotic series, to be precise. It's the perturbative and the non-perturbative asymptotic series. Maybe I should call them like that. And the Z's are the asymptotic series. And Z1 also has the transmonomial in it. Okay. And because it also has a transmonomial in it, where are the Stokes? Here. You're expecting these guys to maybe disappear when I write this for Z. And if I write this for Z0, I get Z0 minus 2 Z1. And if I write the Stokes automorphism at pi for Z1, I get Z1 plus Z0. So, I like this. This is much simpler. And now I know how the Stokes automorphism acts on my trans-series blocks. He said, trans-series? What was the trans-series? The trans-series was just the, general solution to my linear second-order differential equation. That's one solution. That's another solution. I have my trans-series parameters, and that was the trans-series. Let's compute the Stokes automorphism on the trans-series. But let's actually do slightly more sophisticated thing, or less sophisticated, I don't know what you want to call it, but something which looks slightly simpler, which is, let me see if I can find that formula. I wrote it at some stage. Yes, that the Stokes automorphism is quite useful because it tells me how to relate the left and the right resummations. And I had already implicitly said that it was going to lead to Stokes phenomena. And now we can see that happening explicitly. So let's compare left and right resummation dictated by the Stokes automorphism on, where is it? On our trans series for the Quartic integral. Let's do that. Well, if we do that calculation, we have all the information here. So if we do that calculation, we find that S0 plus on curly Z is equal to S0 minus of curly Z, where sigma 0 kept fixed and sigma 1 jumped by the Stokes coefficient. Oh, look, this is really simple. And what about, let me leave that one there. What about if I do the same at pi? Well, I get the resummation to the right of curly Z, and now it's sigma naught that jumps. And there you go. We have managed to show how, okay, example is trivial, but anyways, we've managed to show how looking at Borel singularities, we abstracted ourselves to alien derivatives, and then we exponentiated them with the Stokes automorphism. And when we do the whole calculation, the Stokes automorphism tells us how to relate left and right Borel resummations, and voila, Stokes phenomenon. Linear, easy, but still nicely appearing. And that's not the whole story. I mean, you can actually do a slightly, here's another a homework problem, which is you can't compute what happens when I rotate around the origin. And it turns out that when you look at what's going on with all these guys here and all these jumps, maybe let's try to see if I can get. There's a sort of an orbit in moduli space of trans-series parameters that if you go 4 times around, this becomes the identity operator. So here's a plot you can try to do. Let me share. What shall I share? Let me share. The plot here is actually nice. I can just to share something of. I think you're probably seeing the physics reports right now, and you can try to see how you're seeing the physics report. I hope, right? And you can try to see how I'm rotating. So the notation is not exactly the same as I had before, but we're doing 0 pi 4 rotations. And here's what happens with the resummation of the trans series. And you can see, I mean, of course, it has 2 exponential scales. So it's hard to see. This is a log plot. You see, there's 5, 50, 400, 5, 50, 400, 5, 50, 400, and so on. So it's a log scale because of this exponential difference in scales in the trans series. You can see the 4 rotations. The color code is exactly the same. And those are exponentially suppressed little thingies close to the origin, and you can still see all these loops going around. So it's very neat to see how all these things are working very nicely. And let me just share Mathematica, if I can find it here. Share Mathematica. And there's a plot here as well. And you see that Roberto wrote, do not run in real time. So I'm not going to even try to do it. And you see here also these plots. But you can try to make these plots and see them in a very simple example. Okay, so I hope I've illustrated most of the basic ideas. Let me illustrate one more idea, which is asymptotics. Let me go back to the, and by the way, are we done with the 2 hours, Monica, or not yet? Should I stop here, or do I have another little bit?
Well, the break ended at 32, so.
Okay, so another 10 minutes, or not. I'm not even sure if it's.
Up to you.
No. Please tell me what is the standard thing. Is it 1 hour or is it not 1 hour?
We adapt to the speakers. Some speakers finish early, but most of them go even half an hour over. So
No way. No, I want to do.
So just stop whenever you find a good place to stop.
Okay, then 5 more minutes and that's it. I mean, certainly I hate going over time. So, but you need to tell me exactly what overtime.
There's no definite overtime.
Then whenever I finish, I'll say, yeah, probably went overtime. Okay, let me just make a comment on asymptotics then, and that's it, and then we stop. And this was basically half of what I had planned to do today. So, anyways, let's go back. So I'm sorry of going also particularly slow, but again, hopefully for the students among you, this is of help, I hope. So let me just finish with a comment on asymptotics. Okay, so just I'll be very brief here. So we've already, I think, convinced ourselves that this looks like a reasonable thing. The Stokes automorphism is telling me really what is the difference between the left and the right resummations. I even showed you a very neat plot. Going 4 times around the origin, everything looks quite neat. This, of course, can be written in a slightly different way, just for motivation, which is to say that I can look at the difference, not necessarily understanding how to jump from left to right, but what's the actual difference between left and right. And I can write it like this, which defines the discontinuity across the Stokes line. So I'm basically defining this guy. And the discontinuity is basically the identity minus the Stokes term. Now, why would I be interested in discontinuity? Because I can try to apply basically Cauchy theorem to this discontinuity, to this jump. And so if I just do Cauchy, and basically, well, let me make a plot of what I mean by Cauchy. I am on the complex plane. I have a cut here, which is some discontinuity. And I have some point there, which doesn't matter what it is, whatever I pick. And I just write Cauchy integral formula there. And I just then deform it to the jump of the discontinuity. Okay. So, I mean, I'm making an elementary remark. And if you do that, then you can write down that f of x is -1 over 2 pi I, the integral from 0 to exponential pi theta. The theta would be the angle at which that cut is placed, dw of the discontinuity in theta of f of w. For any f, doesn't matter. And now let's apply it to our z. Where is it? Okay, now let's apply it to our asymptotic series. And of course, we can't do this because we've already computed Stokes automorphisms for both of them. There they are in yellow. So when I apply this to my green power series, the knowledge of Stokes automorphism in yellow immediately tells me how to write the Cauchy theorem in this integral representation. And what I get, okay, let me write this in two steps, just one, it takes 1 second, so I'll take 1 second extra. I can write down something that looks like that. I have an asymptotic series. Let me do it just for the 0th sector now. And because it's an asymptotic series, I removed it. Oh, the screen froze again, right? Did the screen freeze?
Yeah, we cannot.
Okay. Let me just restart it. It's only when I look at my. I'm not sure when it froze. I hope you were seeing what I was. I apologize for this. I don't know what's wrong. Oh, now we have a problem. It's not connecting. What happened here? Let me try again. Sorry about that. Otherwise, it's not a problem. I mean, in worst case scenario, given it's one formula left, I can just do it with a slide. Let me just try once again. Otherwise, we move to. I prefer to do it on the screen. Now it's working. Okay, good. So I just apply this to Z, and what I get here on the right-hand side. So as I said, I moved from equal sign to asymptotic sign because I have an asymptotic series on the left-hand side. And on the right-hand side, I have something that looks like this. That's plus infinity. 2, that's the Stokes coefficient, w minus x, it's over there. Then there's an exponential times this series here. And now, just look at it. I mean, I have to do this integral in W. And somebody should have complained, but I understand my handwriting is small. That should have been a W there. 2W. In W. In W. And by just expanding this guy, what I have there, it's basically a monomial times an exponential integrated over the positive real axis. That's a gamma function. And so this immediately yields the integration of this guy, the following large order formula. So you see that now I can just go. So what do I have? Let me just point out a couple of things. I have my Stokes coefficient. Well, minus, I guess, is also part of it. I have the leading factorial growth. I have the subleading exponential growth, which is the instanton action. And now I can see the resurgence of the full one instanton sector by looking at next to leading, next to leading, and so on. Just to make a little bit of an expansion here. This is -2 over 2 pi I. This is n minus 1 factorial an z01 plus z11 a n minus 1 plus n minus 1 n minus 2 z21 a squared plus so on and so forth. So again, I have my Stokes guy, I have the leading factorial, that's sort of predicting large ordered growth. And then I'm doing sort of decoding of my non-perturbative sector because I can find buried deep in the large order everybody else. And I can actually test this. Let me just finish with that. Where is mathematics? There you go. I think Roberto did this. You can check coefficients. So here we have the coefficients of Z0. And we're trying to see what does large order predict that there will be. I'll be more specific about these things on Monday. But so that would be the prediction of, I'm not sure what he's testing here, maybe the instanton action. And I'm trying to see, that would be, the expected instanton action would be that line just below 1.415. This is what large order is giving me with, let's see, how many data is he using here? 100 guys. And then I do, there's a numerical scheme of acceleration known as Richardson transforms. I guess that should be capital R. Richardson transforms, and you can Richardson transform and accelerate convergence. You lose a bit of data here, but convergence is accelerated. And you see that everybody is on spot of what was supposed to be. And in this way, you have very big confidence that you've just found your large order data. And so this is also a very hands-on, and it sometimes can be quite dirty hands-on because you really have to do a lot of numerics to find and to decode all your non-perturbative sectors that you can see through Resurgence. Okay, so I think I will stop there. So I still wanted to do sort of the more mathematical formulation of these things. I will do this on Monday. Then I wanted to talk a little bit about the non-linear. So I mean, I gave again simplest possible thing I could think of today. So this was sort of the partition function of a quartic integral. You can consider the free energy, which is a non-perturbative problem instead, because it's the log z, so it satisfies nonlinear differential equation. I'll show you that next time. Talk a little bit about the nonlinear problem. And then I will talk about, as I said, that was the plan originally. I'll talk about more generic structures, and then I'll go on to applications. But so for today, I hope I was as basic as possible, and I'll stop here. Thank you.
Okay, thank you very much, Ricardo. So let's give him a